Hi everyone, today I'm going to be giving a quick introduction to TLC. So you might be wondering, what is TLC? So TLC stands for thin layer chromatography. We'll come back to that later. Basically what it is it's a lab technique that you use to separate compounds or mixtures and also make comparisons between them. It's a relatively quick and easy way to do this, so it has some pretty interesting uses in the medical field that I might be getting into a little bit later. So to start out, I'm just going to be introducing you guys to some of the big parts of TLC. So first of all, there are two main parts of TLC that are referred to as the mobile phase and the stationary phase. So to start off, the mobile phase is the eluent. So what the eluent is it's a liquid that you're going to use. First, let me introduce you here to actually the stationary phase first before I really start getting into that. So the stationary phase is the silica plate. It's called the stationary phase because it's the part that doesn't move during the actual procedure. So basically the mobile phase is the eluent, which is a liquid which starts from the bottom and moves its way up through capillary action, which I'll be getting into in just a moment. And what it will do is it will move your desired substance up the stationary phase, and then I'll get into a little bit as well what exactly causes separation to occur. But to start out, just remember mobile phase, that's the eluent, which is the liquid that's in the bottom of the beaker, which you're going to see later, and then the stationary phase is the silica plate. So capillary action, that's another thing that you're going to have to know. That's the mechanism in which the eluent and the substance that you're testing moves up the plate. So capillary action, what that is it's the movement of liquid against gravity up a very thin tube. I'll call it a tube. It's a little bit more than that in general in terms of what capillary action actually is. But in our case, we can think of it as it goes up the plate, kind of through a tube. Anyway, so our next terms, RF, this stands for retention factor. So that's actually going to be what we use kind of to measure what exactly we have. And basically what that is, it's the distance that the substance moves up the plate divided by the total distance the eluent travels. So we're going to get into this a little bit more once I actually start with the experiment. So this is going to make a lot more sense. So I'd like you to just kind of remember these terms and these concepts I'm introducing before we start everything up. And then one more thing, what forces are at play? Of course, this stuff doesn't just happen through magic. There are different things that occur at a molecular level, which actually accounts for the separation that happens between the actual substances that you're testing. So the gist of it is that the silica in the plate, that's this right here. It interacts with whatever you put into it through dipole and hydrogen bonding, and what that means is the higher the polarity of the substance you have, the more the oxygens are going to push down against the flow of the capillary action with your tested substance. So what that's going to mean is that, going back to retention factor, a more polar substance will end up, I don't know, maybe here or here, while a more non-polar substance will actually end up there. Real quickly, we're going to go over, maybe a little scenario that we're going to be doing today in terms of the actual example and demonstration of this technique. So basically, our task is to identify an unknown mix of analgesics, which are painkillers, that an emergency room patient claimed to have taken prior to hospitalization. So our hint is the patient said, you know, I either took aspirin or ibuprofen, and I don't know, maybe it also had some caffeine in it. It was a caffeine and ibuprofen or caffeine and aspirin tablet. And then they go ahead and they hand you some, I don't know, crushed up pills that are all, you know, you can't really identify it off of some website or anything like that. So what you're going to want to do is set up a plate. We're going to be setting up a plate ourselves like this in a minute. So this is where you are going to put your sample of the unknown substance, you know, the crushed up pills that that your patient gives you. And then you're going to get samples of aspirin, ibuprofen, and caffeine, and you're going to put them there. In just a moment, we're going to get everything set up, and I'm going to give you a real-life example of this. Alright everyone, we're going to get started with the actual experiment now. To start, what you're going to need, capillary tubes, just your normal glassware, large beaker especially is good for the actual, you know, mobile phase and stationary phase interactions. You're going to need, in our case, we have 4 different things that we're going to be putting on the thing. The 3 analgesics and then the unknown mixture of analgesics. These are all dissolved in methanol because that dissolves all of them and goes well with the experiment. I'm not going to get into too much detail about that since we don't have much time, but it's important to note that you want something that will dissolve all of your substances. And then for the eluent, ethyl acetate, again, dissolves all the substances. You would usually pick an eluent. You try a few different eluents to make sure that you get the proper separation, but in this instance we already know ethyl acetate works well, so we're going to just be assuming that it's going to work well again this time. Anyway, so to start off, what you're going to want to do is draw a straight line near the bottom of your TLC plate. It doesn't matter exactly where, considering this is going to be the starting point for your substances. You can just pick an arbitrary point, but yeah, near the bottom, straight line is what you want. Since we're testing 4 things, 4 little dashes, we're just going to do one letter labeling. U for unknown, C for caffeine, I for ibuprofen, and A for aspirin. Alright, the next thing we're going to want to do is get the capillary tubes. Alright, well I'm going to real quickly demonstrate how to successfully transfer the substance onto the TLC plate. So what you're going to want to do first, get this capillary tube, just dip it right in there into your sample. Some of the liquid's going to go up via capillary action, and you're going to want to go and press the tube right on the line where your dash is, and you're going to see hopefully a little circle of moisture right there, just about that big, I'd say. You can still kind of see it. Is about the perfect amount to get on the plate. Too much and you're going to have a big smear, and it's going to be difficult to tell exactly where it should be. Too small, you're not going to be able to see it. Just about that size, just about a little bit smaller than the circumference of a circle that would be encompassed by that line right there. Now, real quick, I'm going to just buzz through the rest of the adding the substances on real quick. Alright, now it's time for the part where the actual action happens. We're going to put the stationary phase into the mobile phase now, and we're going to hopefully get a good look at the mobile phase moving up the stationary phase, and then we're going to talk about RF again, and we're going to do our final analysis on the situation. Alright, so now that that's all done, what you're going to want to do is make a pencil marking right where the water line, or not the water line, the liquid line went up to, which is right about here. In our case, apologize for the horrible line, but you should get the idea. Anyway, what we're going to do next is we're going to visualize it in UV light. Alright everyone, so here's the visual of the TLC plate under the UV light. So this is actually how you visualize what you get. The UV light will show spots on where your samples actually move up. Unfortunately though, it doesn't look like we got a super great result. This is just something that can happen with TLC. You make some mistakes. You know, sometimes some unpredictable things go wrong, but we can still take some lessons out of this. So you see some very light markings right about here. Circle them real quick there, and then right on the C there. And then you can see a light marking right there. And then there's some up there as well, and then just about there. It's very, very light, difficult to see on camera. But I'll make some circles about where they are. And then of course there's also a very, very small one right there. And then we're just going to analyze this like we got good data. So basically, we can tell some things about what it could be. I actually do know what the unknown is, so I can show you how it is somewhat consistent with what it actually is in just a moment. Alright, so we're going to real quickly go over exactly how we can analyze this. So first of all, calculating the RF values, I've made little marks with the measurements on where things are. So the RF calculation is how far up the sample goes, so where the circle is basically, divided by the total height that the eluent rose up the column, which is going to be that 4 centimeters. So real quick, I did the RF calculations for basically the 3 general heights that we got. We got 1 centimeter, 0 centimeters, and then 3.75 centimeters. So those are the RF numbers right there. So one good thing is that we did have different substances that had the same RF number. As you can see, the unknown actually had all of the RF numbers, which is usually a good thing when you can match the unknown up to 1 or 2 different things. But unfortunately, what kind of killed the what we're actually getting as a result is that our ibuprofen and our aspirin ended up being about the same height. So we can't really differentiate between whether the unknown is aspirin or ibuprofen. But as you can see, it does match up right there with the caffeine pretty well. So you can say pretty certainly that it does have the caffeine in it, and it has either the aspirin or the ibuprofen. The unknown actually ended up being caffeine and aspirin. So as you can see, it is actually consistent with that. Unfortunately, the fact that the ibuprofen's at about the same height kind of stops you from being able to definitively say whether that's the case or not. But yeah, this is definitely why you should double check with what eluents actually work, because this was an eluent I used a long time ago in a previous lab, and we ended up just assuming that it was going to work again. But you really should check beforehand to see if you do get the proper separation that you're looking for with what you're using. So that's one thing. It's good to learn from mistakes. So hopefully you guys learned at least a little bit from this explanation, and hopefully you learned a lot from certain mistakes that we might have made. So thanks for watching. Please like, comment, and subscribe, and have a great day.